Hello everybody, this is Brian. I'm here to give a little demonstration of some of the descriptive statistics features of StatPowers. Um, so we're going to look at really what you can do with, you have a bunch of numbers and you want to describe them in some way. So look at measures of central tendency, which is a very popular thing to do in statistics. Maybe look at a histogram or a chart. Okay, so I'm going to just paste in some numbers. First of all, when you come to the website under analysis, you'll want to go to quantitative one sample. So quantitative meaning this is numerical data, okay, numbers, and one sample, just one group of numbers. Now you can enter data in a bunch of different ways. You can, as it says here, you can separate them by comma, semicolon, space, new lines, tab. It's very flexible. I'm going to just paste numbers separated by spaces. You can title the data set if you want to, but you don't have to give it any title at all, really. And I'm going to just click calculate now. When I do that, what you're going to see is these are going to get sorted into increasing order. For a single sample of numbers, there's no, the ordering doesn't really matter, so this goes through and orders it for you. Also, if you had put in some new lines, a couple of semicolons, all of that stuff is just going to get kind of just filtered out, and you can see now it's just clean and going increasing order. Now, under summary statistics, this is where we're going to see like the basic summary statistics that we consider important. First of all, it's telling us the sample size. We have 32 numbers in our data set. The mean, that's the arithmetic average. That's if you add all the numbers together and divide it by 32, that's 5.25. We've got the median, which is the kind of halfway point. If we went to it would be between the 16th and 17th numbers in this in the ordered list. That would be a 5, and you can see that is right in there. Mid-range is calculated by taking the average of the lowest and the highest number. So the 2 and the 8, average of 2 and 8 is 5. Mid-range is taught in some statistics courses. It's honestly not a very useful measure of central tendency. And I don't know why, I just skipped the mode. But the mode is the most common number in the data set, and 5 is appearing most commonly. It looks like there's 11 or something like that, 5s. Okay, so those are all different ways of talking about the center, and you can see this data set is not very skewed. It is symmetric, more or less. So the mean and the median, the mode, the mid-range, all of those are really close to each other. Okay, measures of spread. These are 4 different ways that we commonly describe how much the data spreads away from the center. The range is just telling you the difference between the highest and the lowest value. So the 8 and the 2, the difference is 6, and that's what a range is. The interquartile range is not looking at the difference between the maximum and the minimum, but it's looking at the number that's 1/4, the 25th percentile, which is if you in these 32 numbers, I guess it would be between around the 8th number. That's about the 25th percentile, right? And then the 75th percentile, 3/4 of the way up, is going to be it's going to be roughly the 24th or so number. Anyway, that's the difference between those two. And I think that we have a 5 and a 6, and so the difference is going to be just 1. So the next is the variance. Variance is it's roughly speaking the average squared difference from the mean. this is the sample variance, of course. So it's divided by when the formula is done, it's dividing by 31 instead of 32. So it's not the arithmetic average. It's divided by one less than the sample size, and this is done for a reason that we don't have to get into right now. But this is the sample variance, and then the sample standard deviation, which is just the square root of the sample variance. Now, looking at this, you might be interested in getting more or less decimals of precision, and I just want to show you how you can get that. First off, we'll just go up to this little gear icon. This is settings, and there's only a couple settings. You can change the precision to, like, let's change it to 5 decimal places. Okay, so if you wanted more decimal precision, I've heard one rule of thumb is you should keep at least 1 decimal of precision more than your data set. So because my data set's integers, I would want to have at least 1 decimal point of precision. But honestly, I think probably 3 is pretty good. 4 is nice. Sometimes it really is, but I wouldn't go any lower than 2, honestly, for this. The more rounding you do from your standard deviation early on in any calculation, the more likely you're going to get a very more rounding errors compounding, and you'll see more of that later on. Okay, so other statistics: the minimum, the first quartile we talked about. Oh, it is a 5, and the third quartile is a 6. Okay, and the maximum. So these numbers are often used when you're giving what's called a 5-number summary. The 5-number summary is the minimum, then the first quartile, and then the median, and then the third quartile and the maximum. Those 5 numbers kind of tell you at a glance the shape of the data, in a sense. It tells you, like, if you've got kind of if you got more of the numbers clustered around the middle, if there's a skew to the left or the right, things like that, you can get a sense of from those 5 numbers. But those are also the 5 numbers that go into creating a box plot, which I will show you next. Just wanted to show you this percentile feature. This is estimating percentiles. So this data presumably was sampled from a population of some sort, and if I wanted to estimate what's the 5th percentile from that population, 2.95 is calculated. And there are lots of different formulas for calculating percentile estimates, and they all have pros and cons. I'm using this R8, which I'm using the reference that's found on Wikipedia. It seems to be a very good method. So that's why I'm choosing it. Maybe in the future I'll allow for an option of different methods, but right now it's using that. And if I wanted to find the 35th percentile, just type in a number, 30.35, and hit enter. The 82nd percentile, 6.847. So this really, what it's doing is just interpolating between the 2 numbers in my data set, which would be like the 82nd percentile is going to be somewhere between a 6 and a 7, like I guess. And so all these different methods are just different interpolation methods, and they give more or less weight to, like, the number before and after. Anyway, that's what this method does. Skew is a measure of how asymmetric my data set is, roughly speaking. And kurtosis is kind of a way of saying how much of the probability mass is clustered in the center, and how steep or pointy my histogram is. This is a very, very rough understanding, and honestly, kurtosis is not really talked about in intro stats courses. So these are some of the summary stats. Let's go down to some charts. A histogram is created for me, and when a histogram is created, it's going to choose the number of bars for me. I have the option for discrete data, which is what I have, where the data is just whole numbers. I can get a single bar for each value showing up in my data set. This is usually a very good choice if you have discrete data, as long as the range isn't too high. This looks very nice with a single bar for each data value, and it shows me the frequency on the left-hand side. If I instead wanted to change the number of bars, I have a lot of choices for doing that. I'm going to just scroll through these. A few of these are just rules. Square root of n, which is the square root of the sample size. Then there's different Sturge's formula, Rice-Doane's formula. I mean, these are all well-known formulas for calculating the optimal number of bars, which, they have their pros and cons. It uses Freeman Diaconis's choice, which as a default, but you can change this to specify 4 bars, 5 bars, 6 bars, 7 bars. What you probably want to do is you don't want the bars to be so many that you have huge gaps between them. So for this data set, I think that 7 bars, which is actually the same as discrete data, is probably the optimal shape. If you go too low on your bars, you can lose some of the I guess resolution, like some of the shape is lost. This actually preserves the shape of my data pretty well, even at 4 bars. But once you go too high, then you may also lose something in there. So usually it's somewhere in the middle, and you probably want it to like look pretty decent. Like this is fine. Choosing the number of bars is a bit of a trial and error, or a bit of an art, I guess. Okay, so a box plot I mentioned before. A box plot is it's a way of displaying that 5-number summary. The minimum, the first quartile, the median, the third quartile, and the maximum. Now, there's actually a little bit more you get from a box plot. You see some dots, and then you have this, what we call a whisker, and then we have this box in the middle. You'll notice first of all, you'll notice the box has a dark bar right here on the left. That dark bar is the median. In my data set, it just so happens that the median is the same as the first quartile. So this rectangle is a rectangle that goes from the first quartile to the third quartile. And because the median is equal to the first quartile, that dark bar is laying on top of that left edge of the box. Okay, that happens sometimes. Then you have these whiskers that go out up to the upper fence and lower fence. And upper fence and lower fence is really just, this is the highest and lowest point of data that is considered to be a non-outlier. An outlier is calculated by going as far from the box as one and a half times the interquartile range. Remember, the interquartile range is the interquartile range is the distance between, it's the width of the box. So if you take the width of the box and go 1.5 times that up above and 1.5 times that below, that's giving a bounds for non-outliers. So anything beyond that is going to be considered an outlier. We have an outlier 2, 3, 8. Those are outliers. So this is a simple demonstration of my data set, or a simple chart. Okay. Now I'm going to just show. I'm going to copy in some data that is decimal data, and we'll see how things might look a little bit different. So I'm going to clear and paste in this. I'm not even going to bother naming it. Let's calculate my stats. Now, in this case, there's no mode because because my data it's like continuous data, it's not integer data, it's unlikely that you're going to have, any precise decimal occurring more than once. So there's no mode. There's no number that occurs most often. Everything is occurring once in my data set. If there were multiple modes, they're going to be listed. And I would say if there's like more than 2 modes, then the concept of mode is not really going to be a useful concept. It's not really applicable to a data set. Once you have like 3 or 4 or 5 modes, just because you happen to have repeated numbers the same frequency, you can disregard the mode and say the mode is not applicable to this data set. StatPowers will not do that for you. StatPowers will list all numbers that occur the most number of times will be listed here as modes. So it's up to you to make the decision that mode is not applicable. But I'm going to show you what the histogram might look like for this data set. I can't use discrete bars because my data is not discrete. And my Boxplot looks a little bit different. Here, I think it's much more apparent that my data is skewed to the right. You can see like in the interquartile box from Q1 to Q3, you can see the median is much closer to quartile 1. The data kind of is spread out much further on the right than it is on the left. Does that make sense? You can see, and even you have some outliers on the right. This is an indication that you have a positive skew. You actually see that in the histogram as well. The positive skew is the kind of pulling of the data tail. This is what we call a tail. This tail going off to the right. And if you went under summary statistics, you'll see the skew is positive 1.242. Positive skew means that it skews to the right. Same thing. Okay, so this is some of the simple descriptive statistics features that we have for a single sample of data. I hope you had fun. All right, bye.